Warm welcome to everybody. This is part 3 of our ongoing webinar series on heat pumps, brought to you by the Northwest Net Zero Hub in collaboration with Stiebel Eltron, who'll be delivering today's technical presentation, as we have done on the previous sessions. Don't worry if you've missed earlier sessions in the series. They've all been recorded, as this one will be. The Northwest Hub, our aim is to provide free independent technical advice to local authorities nationally. Our hub covers the Northwest, and my role within the hub as the estate decarbonisation lead. John Mullins, supported by Namitha. We're hosted here in Liverpool by the Liverpool City Region Combined Authority, and that's why you may see emails coming out from us, coming from Mersey Travel or something like that. So just be aware that's what the linkage is. They support us, they give us a home and provide us with IT services and things like that. This webinar series is one of the ways in which we support public sector organisations in really helping build knowledge, sharing knowledge, building confidence in low carbon technologies. Heat pumps are a huge topic, so we've broken the series into six parts. We've done series 1 and 2 already. Today we're going to look at understanding heat pump systems, and to come will be commercial, maintenance and repair, and then a summary overview. For all of those sessions, we'll send out registration links in advance, as we did with today's session. Stiebel Eltron, why are they presenting? We are supplier agnostic. We're not endorsing them in any way, but they do, however, have a large facility right next to our offices here in Liverpool. They're based over the water in Bromborough, and they've got a long track record in this. They're a 100-year-old German company. They've had over 50 years doing heat pumps and ventilation systems, that type of thing. So a lot of experience. Matt Fitzpatrick, their lead here, lots of experience in both training people on heat pumps and specifying and designing heat pump systems and broader renewable solutions for both the residential and commercial section. So that's who we are. That's what we're going to do. I'm going to hand over now to Matt, because Matt is going to take us through the detail of understanding heat pump systems. And we'll have a space for Q&A at the end. So if you've got questions, drop them in chat and we'll pick them up at the end. Thank you. Over to you, Matt.
Thank you very much. So in today's segment, we're going to look at understanding heat pump systems, what's involved, what type of components, and also do a little bit of myth busting. So we'll look at the system components. We'll have a look at system design, so multiple heat emitters, underfloor and radiators. We'll look at domestic hot water cylinder sizing, a brief look at buffer cylinders and bufferless systems, and pipe sizing and pump sizing. So first we'll start with system components. I've put some of the more common system components on the slide. So we have what we call our WPM controller. In the industry, this is normally a heat pump manager or an interface. This is the main control platform for the heat pump. It will allow you to enter commissioning parameters, time schedules, domestic hot water temperatures, and heat curves. There are other aspects as well, such as being a wiring center, so you can connect pumps, circulation pumps, sensors, mixing valves, other components directly to the manager. This makes it a lot easier when you're trying to design a very confined plant room. Next up, we will have a room thermostat. So we have our FET room thermostat. Now, most heat pump systems are normally operating on a weather compensated curve. The colder it gets outside, the more energy the heat pump puts into the property and into the system. But we all like different temperatures. You speak to different people and people are happy at 18 degrees, 20, 21, 24. So we need to ensure there is a balance in the property. Now, having the room thermostat allows us to not only override the weather compensated curve with a marginal factor, but also provide the higher comfort levels that we're used to with fossil fuel heating systems. In the top right, we have what we call our internet service gateway. Now, this is remote monitoring. It's a remote connection to the heat pump system. This will allow us to remotely diagnose the heat pump system. It will allow us to change any parameters remotely, see if parameters have been changed at the controller, and revert it back to its commissioning parameters with the click of a button. It's exceptionally useful and time-saving because you don't need or require an engineer to go to site for every given inquiry. You can look online. So it's vitally important to ensure in this day and age that your renewable system has some form of remote monitoring, remote logging to be able to access the system without having to go to site. In the system, you'll normally find primary loading pumps. So highlighted here on the bottom left. Now, these pumps will take the energy from the air source or ground source heat pump to the buffer cylinder or the domestic hot water cylinder. So the two main cylinders for the system. It's crucial to get the pump size correct and also to ensure the pumps are efficient. So you don't want to install a very large oversized pump if you don't have to. And there is modern technology which is called PWM, so pulse width modulation. And this ensures the pump is operating at the correct speed. Now, you'll need to ensure that your heat pump manager or heat pump controller has the facilities to operate a pump via PWM. It is greatly beneficial. You can see up to 10 to 15% increase in efficiency on most systems with PWM pumps. Now, looking after the buffer cylinder, moving towards our radiators and underfloor, we have what we call in the middle here a WPKI or a heating circuit loading station. The idea is to be able to take the energy from the buffer cylinder and deliver it to the radiators and underfloor efficiently. But we also need to keep in mind we need to conserve space. We don't want to have a large room full of pumps and pipes and sensors. It is domestic, so we need to keep it quite small and compact. But also, when we're looking to size radiators and underfloor, it's all done through flow temperature. Radiators will naturally require a higher temperature. So on average, it's around 45 degrees, whereas underfloor could be as low as 28 to 35. But we have a buffer cylinder held at 45 degrees in this example, which is the perfect amount of energy for the radiators, but it's too much for the underfloor. So inside the loading stations, you will have a mixer, and this allows us to blend the temperature down alongside the heat curve. So the underfloor can receive 28 degree flow temperature and the radiators can still take 45. And then there are manifolds to be able to connect these loading stations in a nice linear platform on the wall. So system design and multiple heat emitters. So in this example, we just have a hydraulic diagram. We have our air source heat pump on the left with the flow and returns going to a buffer cylinder and also flow and returns going to the hot water cylinder. In this example, there's only one heating circuit. So this could be underfloor or radiators. We're going to target one temperature in the buffer cylinder. So this could be, it depends on the heat curve, the heat curve and weather compensation, but we'll say the maximum temperature is 38 degrees. So there's only one temperature to be delivered to our heat emitters. And this could be underfloor or radiators. Now, buffer cylinders, if you have one heat emitter type, you can go bufferless, which means you do not require this cylinder here. But there are a few scenarios and key points to take away, which we'll cover in a couple of moments. So when we have two heat emitter types, radiators and underfloor, we have to cater for the largest or the highest temperature. In this case would be 45 degrees for our radiator circuit. So we will target the buffer cylinder at 45 in this instance, but our underfloor circuit on the right hand side only needs 38 degrees. Well, we can't ask the heat pump to deliver two different temperatures because we only have one vessel to store the energy. So the buffer cylinder then provides what we call hydraulic separation. We have our energy source and our volume, and then we have two individual loading stations to be able to extract the energy from the buffer at the determined temperatures, so 45 and 38, without causing any problems to either heat emitter. Now, the reason we do this, underfloor and radiator heat emitters have different flow rates. And if the flow rate passes through a heat emitter too quickly, there is not enough time for the heat to be deposited or delivered into that room or the area. So it's just speeding through the system and returning back to the cylinder, which can then cause faults or problems with the air source heat pump, because it's a natural balance. The heat pump is loading the buffer with temperature, and the heat emitters are extracting the temperature from the buffer. If there is no extraction, the heat pump will overheat the buffer cylinder and then switch off in a fault. So that's the main reason why you would normally have a buffer cylinder with two separate heat emitter types for that hydraulic separation. Now, buffers can range in various sizes, so this diagram is just an example. They're not normally as large as these tanks. So I've mentioned the phrase bufferless system. You may have heard it before in the industry. Effectively, it means there is no buffer cylinder. The heat pump is supplying directly to the underfloor or radiators. Now, in this type of system, we can't mix and match heat emitters. Again, going back to the previous comment that we need hydraulic separation, and we also need a variable in temperatures, two different temperatures. So it can only supply underfloor or radiators. And in most cases, it needs to be kept as open loop. So for example, if it's radiators and it's a bufferless system, the TRVs, thermostatic valves, are removed and lock shields are installed to ensure a constant flow around the system. And if it's underfloor heating, same scenario. The actuators are removed, there are no additional controls, and the heat pump and the underfloor run at a constant flow rate, always sending the flow around the underfloor, and a temperature is delivered via our heat curve. I will also mention, when it comes to having a buffer cylinder or a bufferless system, PWM pumps are beneficial because we focus on something called a delta T, a difference between the flow and return temperature. So the flow is indicated here as the red line on the diagram, and the return is blue. Now, the optimum number for heat pumps to operate at their highest efficiency is around 5 degree delta T, difference between the flow and return. We can push that to 7, so you have a window of 5 to 7 degrees. Now, on a bufferless system, or bufferless heating system, or a heating system with a buffer, it's very easy to achieve this delta T of 5 to 7 because we have a large volume of water to be able to balance the flow rate. Now, PWM pumps become really beneficial when we look at domestic hot water and heating, because the pump speed and flow rate required for the heating will be completely different to the domestic hot water. And this is because the domestic hot water cylinder has a bigger pressure loss. There is a coil inside the cylinder that we need to send the energy round the coil and back to the heat pump. And because there's a bigger pressure loss, greater force is required, which can then change the flow rate, in most cases drop the flow rate. So the PWM controls allows us to set the set delta T for for hot water, so this could be 7, and then for heating. In most cases, we use a 2-pump system, a loading pump for the heating system and a loading pump for domestic hot water, to allow us to have PWM controls on both. If you were to use a diverter valve, then you may fall foul because you may set the flow rate for your heating, but then the flow rate that you've set on a singular pump isn't sufficient for your domestic hot water. However, because we're targeting higher temperatures in the hot water cylinder, we need to ensure that delta T is the best we can possibly get it. Otherwise, we have a backlog of energy of heat that cannot reach the cylinder and transfer into the domestic hot water, and will return back to the heat pump, which means short run cycles and potentially faults on the controller and the heat pump. So domestic hot water cylinder sizing. Just a couple of points I've taken from the MCS 2025 heat pump design standards. So one key point is 3.5.5, which is when installing a domestic hot water cylinder to work with the heat pump must be capable of at least a 55-degree flow rate. And that's to be able to bring the domestic hot water cylinder up to 50 degrees. And then when we look at sizing domestic hot water using the MCS 2025 heat pump design standards, on average, it's 45 litres per person. So a simple calculation could be a 3-bedroom property. So let's have a quick look. 45 times 3 would give us 135. Now, in a 3-bedroom property, there could be a main bedroom, so 2 additional people equaling, or sorry, 1 additional person equaling 4. So I always add an additional 45 litres, which means that cylinder capacity is 180 litres, which is what would be required. It's also crucial to make sure that the coil size is correct for the heat pump output as well. And with a cylinder of 180 litres, you need to ensure it's a heat pump cylinder, because if the coil size is too small, again referring to the previous slide, the heat pump cannot deliver the energy required and it will go out into a fault state. The equation is for every kilowatt output from the heat pump, you need 0.25 meters squared of coil size. So if you have a 10 kilowatt output, the coil size needs to be 2.5 meters squared in that domestic hot water cylinder to be suitable for that heat pump. So taking some of the design standards, we'll just have a look at potential cylinder sizes for various size properties. So a 3-bedroom property, as I've mentioned, is 180 litres. A 4-bedroom property is 225 litres. A 5-bedroom property is 270 litres. And a 6-bedroom property is 315 litres. Now, this will all depend on the property. This is a rule of thumb. If a 4-bedroom property has 2 baths and a shower, I would probably be looking closer towards 300 litres, because we have 2 baths that require 80 litres per bath and a shower, and there may be 2 baths operating at the same time and then someone has a shower afterwards. So you need to always prepare for the worst case scenario. But it doesn't always mean installing a bigger or larger capacity cylinder. When we look at the energy and temperature we actually need in a property for domestic hot water, we are fixated on having 60 degrees at kitchen sinks and coming out of bath taps. It's not required. It's an unusable temperature. It's far too hot. We blend it down to around 45 degrees for kitchen sinks, between 40 and 45 degrees for baths, and around 38 degrees to 40 for showers. So we can achieve a greater mixed water volume. And this has been highlighted at the bottom. So if we take, for example, our 225 litre capacity pre-plumb cylinder, and we held the cylinder at 55 degrees, and we only required a mixed water volume of 45 degrees, then we can achieve 300 litre capacity, which would cover a 3 and 4 bedroom property if it's a single bath and a shower. So it's not always about the size of the cylinder, it's the energy we can get out of the cylinder and how we can modulate it. Buffer cylinders. So compared to the fossil fuel heating systems, they do not normally require a buffer cylinder unless it's a large domestic, potentially, not domestic, commercial project, or there's multiple heat sources going into the heating system. So with renewable heating systems, a buffer cylinder can be required or may be required when you need to ensure you have sufficient volume for defrost cycles. I think I've mentioned this in previous segments, but I'll just recap. So in the heart of winter, when it's very cold and very humid and the air source heat pump is extracting the energy from the air, it can pull the intake air exceptionally low to 0, -1 temperatures, which means any water droplets on the evaporator can freeze, and the heat pump runs in reverse to thaw out the evaporator. If we do not or cannot achieve sufficient system volume to complete a defrost cycle, we then need to have a buffer cylinder. Now, in some cases, defrost cycles can occur once or twice an hour, and with some systems can take up to 80 litres away from the heating system, which is a large amount. So that buffer cylinder provides us with a protective layer of not only volume, but a minimum temperature of around 18 degrees to ensure that if the heat pump has been off overnight and the first run cycle is domestic hot water, it requires a lot of energy from the air. It may potentially need to defrost, but there is a thermal store or mass of energy that the heat pump can use to complete a defrost cycle rather than going into a fault. It's also there to provide hydraulic separation from different types of heat emitters. It also means you can have multiple heating circuits. For example, our heat pump manager can control 3 to 5 different heating circuits, so 5 different pumps. For that scenario, we would have a buffer cylinder to cover 5 stories of a property. So we look at buffer cylinder sizing. So we need to consider the following points. What's the minimum size required? Well, always look at the manufacturer's recommendations. They will know how much volume their product will need. For example, ours only require larger, probably say the most is 100 litres for a single system. If it's bufferless, it is slightly less. So the buffer cylinder is there and it's in line with the manufacturer's recommendations, which means there are no problems with warranty, servicing, repair, or the longevity or operation of the unit. And second of all, it's the kilowatt output of the heat pump. Now, the greater the kilowatts output, the larger the flow rate. So we have a large volume of water passing through. And the example I always use, we have an 87 kilowatt ground source heat pump, very commercial heat pump. And that will deliver 89 kilowatts at a flow rate of around 259 litres per minute. So as an example, the buffer cylinder on the left-hand side is our SPP 100 Classic, so it's a 100 litre buffer cylinder. And on the right-hand side is our STH 720 Plus, which is a 720 litre buffer cylinder. In the example of the 89 kilowatt ground source heat pump, trying to deliver 259 litres per minute through a cylinder, which is half this, or more than half the size of the volume coming from the heat pump per minute, it's just not going to work. It's going to cause problems and faults because it will restrict the flow. And we have the backlog of energy. So then a larger buffer cylinder would be better suited, larger tappings and a larger volume to allow it to transfer through to the heating system. And when can we specify bufferless systems? So we can specify bufferless systems if we have the same type of heat emitter. Excuse me, we can have two zones. So you can have a ground floor and a first floor of underfloor, or a ground floor and first floor of radiators, but they need to be the same heat emitter type or the same flow temperature. So if the radiators can be sized to 38 degrees, sorry, no, my apologies. Yes, so it's the same heat emitter type, so they have to be underfloor or radiators. Even if you size the radiators to 38 degrees, the same as the underfloor, you will still have different flow rates. So you would need to have a buffer cylinder for that system. You can also use bufferless systems when space is short. You haven't got enough area to install a buffer cylinder, but you'll need to keep an open volume. Now, for our larger units, it's 40 litres, and the smaller 7.5 kilowatt units, it's 20 litres of volume. So that's a couple of things to bear in mind, that we need to keep a set amount of open volume for the air source heat pump to be able to complete defrost cycles, and a minimum temperature of 18 degrees. And we can't mix and match heat emitter types. It must always be open loop and one type of heat emitter. So pipe sizing. I will just add, this is quite an in-depth topic, so I'm just touching on a few key points, things that you can use and may be useful moving forwards. There may be some more information coming out about tips and tricks on pipe sizing and pump sizing. So the first key point I always make is the internal bore. There is a big difference between plastic pipe and copper pipe. So the internal bore of plastic pipe is normally smaller than the diameter it's advertised as. So if we look at 32 mil plastic pipe, that is the external diameter. The internal diameter is 27.2 millimeters, so almost 5 millimeters smaller. Now, this can cause problems with flow rates, and it can also cause problems with flow velocity, which makes systems quite noisy. So we need to ensure we get the correct pipe diameter. For copper, the size that's given, so 28 mil or 35, is the internal diameter. So if you order 28 mil plastic, that could be 22 mil or 23 mil internal diameter. So you would need 32 mil plastic compared to 28 mil copper. If you do have flow restrictions, you can start to cause faults with the system. So we call them high pressure faults. It can't deliver the energy, and a noisy system. It's the volume is passing through the pipework too quick, creating excessive noise in the property. So just a small section on sizing circulation pumps. So you must always check the pressure loss of the system. If you have additional elbows and bends in the heating system and the primary system from the air source or ground source heat pump to the cylinders, this will increase the pressure. The pump has to work harder to send the energy around the circuit. But there's also other aspects as well. Heat exchangers. So the heat exchanger inside the air source or ground source heat pump will have a pressure loss because it's a smaller diameter and the pump has to work harder to get it through this component. Any external heat exchangers will have a temperature loss and a pressure loss as well. So these need to be factored in. At that stage, when you have the full pressure loss of the system, you can compare it to what's called a pump graph, which we have on the screen here. You can then refer to the manufacturer to see what their minimum flow rate or nominal flow rate is, normally in meters cubed per hour, and you can see if your pressure loss or your pump can overcome the system pressure at the required flow rate the manufacturer specifies. Now, increasing the pipe size, so say for example you have 28 mil flow and returns on the primary to the air source heat pump and the buffer cylinder. if the heat pump is 20 meters away from the buffer cylinder and you have a high pressure loss in this primary circuit and may require a larger pump, you could increase the pipe diameter to 35 mil, as there's a bigger pipe diameter. There's less pressure, which means you may not need to oversize the circulation pump. So there's two aspects. The pipe sizing is crucial to the pump sizing and vice versa. This goes to the first point, right? So you don't always need a very large oversized pump. If we design the system to the pump's capabilities, we can use a very low wattage efficient pump with a well-designed system, and it's all part of the balance. So I mentioned flow velocity. Now, flow velocity is the rate the water is passing through the pipe. The magic figure we look for, the ideal number, is 1 meter per second or less. So in the examples we have here, we're looking at correctly sized pipes. So on the first example, we have 22 mil pipes, so flow and returns, and we need to achieve 1.5 meters cubed an hour. So that's our nominal flow rate. Now the flow velocity is 1.10 meters per second. So this will start to create noise inside the circulation or the pipes to the buffer cylinder and off to the heat emitters and heating circuits. It also changes the way the temperature is delivered. So if we look at how we can counteract this and we can bring it below 1 meter per second, on the second example, we still only require 1.5 meters cubed per hour. But if we increase the pipe diameter to 28 millimeters, we now have a flow velocity of 0.68 meters per second, which is a lot quieter and a lot more efficient and effective for the system. So that is the end of the presentation. I'm assuming there will be a fair few questions, so I will hand back over to John, who will start the Q&A session.
Right, thanks, Matt. No, that was informative. I think, yeah, if you've got any questions, by all means, drop them into chat. Just to clarify, Matt, a few things that you made there was, for example, where a heat pump has to deliver two different temperatures, for example, to radiators and to underfloor. Is it not the case, just looking at your wiring diagram, that you are effectively blending some of the returning cool water into the low temperature circuit just to be able to get the right temperature?
Correct. And the reason we do this, because the underfloor may not need 35 or 38 degrees at that time. It may only need 28 or 24 alongside the weather compensated curve. So if we use the return temperature from the underfloor and blend in some of the warm or hot water from the buffer cylinder, we're reducing the amount of energy we draw on the buffer cylinder, so making it far more efficient, but also we're only delivering a small amount of what we need. So it makes it a lot more efficient. And it also stops things like actuators opening and closing all the time and a fluctuation of room temperatures in the room.
Okay, thanks. And then you made another interesting statement, which I think some clarifications required on that. If the velocity in the pipework is too high, we don't get proper heat transfer from the radiators, which made me think, surely if a radiator is full of water, irrespective of how fast the water is going around the circuit, that radiator is still going to come up to temperature and radiate heat into the room. Do you want to just explain what you meant by if the water is going too fast?
Yes, so inside the diameter of the pipe, when the flow velocity increases above 1 meter per second, the majority of the movement is in the internal bore, the center of the pipe, rather than the outer aspect of the pipe where the heat can be transferred. So you will have effectively almost two temperatures inside the pipe, one on the outer ring or the outer extremities near the external walls, and a higher temperature going through the center. And it changes the way the water reacts. So it means you will have it passing by too quickly with not enough time to deliver the energy, And effectively what will happen is you start to see a warm return coming back. And it's not delivering the temperature in a sufficient way.
Right. So effectively the water in the pipe, the water against the pipe walls almost insulates the water in the inside of the pipe.
Correct.
That extra layer of insulation. Okay, that's fair. And then apart from gurgling noises in your pipe work, if you go above 1 and we hear noise and things like that, what are the sort of things that people should be looking out for as symptoms of potentially a poorly designed setup and things that should be raising a flag?
So the easiest way to determine a system that's not been designed sufficiently or correctly, you should always have a balance of temperatures. So if you're looking at the flow temperature from the heat pump to the buffer cylinder, through the radiators and back, it should be around 5 to 7 degrees difference at each point. If you are finding you're having 50 degrees flow temperature going to the buffer cylinder and to the radiators, and you're getting very, very low temperature back, such as 10, 12, 15, 20, or it's coming back at almost the same temperature, that's an indication that there is no balance in the system. You're correct, apart from gurgling and noises, you can hear effectively a couple of noises from the pipework. It makes it a lot more difficult to live with, but the flow rate will also be affected. So it means it will not be able to achieve the correct delta T difference between the flow and return. This is crucial. It really is. Fossil fuel systems have a delta T of 20 degrees, whereas heat pumps have 5 to 7. So you can get away with mistakes on a fossil fuel system. With heat pumps, the system needs to be correct.
Which might lead us on to why the heat pumps and the radiators are at lower temperatures. You keep them running continually, because if you do what you do with normal gas boilers, the heating comes on in the evening and then it goes off again and then it comes on again. On each of those times, I assume we get a full system of cold water returning back.
Correct. Yes.
Okay. Yeah. Right. Those were my key questions. If you do have any other questions, drop them into chat. Namitha, if you have any other questions, drop them in. Otherwise, what we'll do, we'll look at closing this one off a little bit early and look forward to the next session, which we'll be diving into. Matt, I think you also raised an interesting comment in our sort of pre-webinar chat. You raised a topic around changes to legislation on room ventilation. Do you want to just talk that one through again? That might be of interest to some of our viewers.
Yes, so there was a new change in regulation regarding ventilation inside properties. It's all to do with mold, mildew, and damp. And that has come into play, I think it was last month or a couple of weeks ago. And it means housing associations and private landlords have, I think it's 10 working days to rectify any concerns or reports of mold or mildew appearing in properties, and then a further 5 days to rectify the issue. There is different strategies to be able to control humidity, mold and mildew, and ventilation. There are passive ventilation aspects such as trickle vents, but we need to ensure that the tenant leaves the trickle vents open. There is ventilation aspects such as centralized mechanical ventilation and heat recovery, which can be quite disruptive. And then there are less disruptive paths such as decentralized ventilation.
Yeah, I was going to say there's a whole world of building ventilation and how local authorities can respond, or housing associations can respond to reports of mold and damp, and it's a big issue, especially with the cladding issues that have been installed incorrectly over the last few years. So potentially we will stick that down as a future topic to add into our education series. So look out for that notification. That would be coming out probably January, February next year. Matt, in that case, can I say thank you very much to you? Namitha, thank you to you for doing the running around in the background, and we'll get this posted up, and then we'll get the invitation to the next one in the series sent out. So thank you to all of you.
That's okay. Thank you very much.